Hello, everyone, and welcome to ACS Webinars, connecting you with the best and brightest minds in chemistry, live from Washington, D.C. I'm Eric Holderman, and I'll be your host during today's webinar, which is being co-produced with the Science History Institute. We'd love to get you involved in the discussion. You can share your thoughts and questions in the questions panel. The slides for today's webinar can be accessed right now by clicking the link that you see in the GoToWebinar control panel. And an invitation email to view the unedited recording from today's presentation will be sent to all registrants for a 24-hour period, after which it will be removed, edited, and posted to the ACS Webinars and Science History Institute websites. Our moderator today is Bill Jasinski, who is a partner in the Unami Group, offering sales support and consulting in specialty chemicals and lubricants. Prior to that, he was a co-owner of Ivanhoe Industries, a specialty distributor that has extensive experience in market and product development. Bill holds a PhD in organic chemistry from Cornell University and a BS in biochemistry from Manhattan College. And with all of that out of the way, Bill, it's up to you.
All right, well, thank you, Eric, and we'll start. Welcome, everybody. We're happy to have you with us and looking forward to an exciting webinar. So our first speaker today is Sergey Kalnos. He's a senior staff scientist at Oak Ridge National Laboratory. He joined Oak Ridge's Material Science and Technology Division in 2009. His interests are in mechanics of materials and numerical simulations of mass and charge transport to improve battery performance and safety. Sorry about the cat. He received his BS and MS degrees in mechanical engineering from Kharkiv Polytechnic University in the Ukraine and a PhD from the University of Nevada. Sergey holds 7 patents and is the recipient of the 2017 R&D 100 Award for the development of the impact resistant electrolyte. He is the co-author of the Handbook of Solid-State Batteries. So with that, I'll turn it over to Sergey and let him go on from here.
Hey, I hope I'm showing my slides well now. And thanks, everyone.
And Sergey, feel free to turn on your webcam.
Okay. Sorry about that. Kind of takes a good portion of the screen, so I'm going to try to move it somewhere so I can see actually what I'm presenting. Thanks for the introduction and happy Pi Day, everyone. I think we have enough nerds in this group to celebrate that. And so there will be 2 presentations on solid-state batteries. I'll open the discussion with kind of basic overview of where we stand and why mechanics is important. And my colleague, Eric Herbert, will dive into more details, especially how to make solid-state batteries work with the metallic anodes. So before going into what solid-state batteries are and how they work and what is the current state of the R&D, a brief overview of conventional liquid electrolyte lithium-ion batteries seems to be in order. And this basic cartoon shows the typical structure of what you find inside liquid electrolyte cell. Despite humongous research on different materials for the anode, graphite is still the most common component constituting the anode in lithium-ion battery, and the cathode typically represented by layered metal oxide. All that is put together with binder on top of the metallic current collectors, and the charge that comes from the external circuit as electrons is carried as ions by the electrolyte. The only thing that separates positive and negative electrode in this structure is the porous membrane, which is promptly termed separator. It's typically a polymer membrane which contains the electrolyte. And the electrolyte itself is lithium salt dissolved in the organic solvents. So we all pretty much aware of the usage of lithium-ion batteries nowadays, everywhere from the electronics to electric vehicles. So I wanted to put some more unorthodox usages of these batteries. One is the NASA spacesuit, which is called EMU. I wonder how many people know what it stands for. I'm going to give you the answer right away. It stands for the extravehicular mobility unit. So it's not an ostrich, it's extravehicular mobility unit, and that pretty substantial lithium-ion battery pack controls the oxygen pump and all the communication equipment, temperature monitoring, what have you, in the spacesuit. And in military, you would be surprised to find out that typically in combat, soldiers have to wear up to 16 pounds of batteries to power up night vision, again, communication equipment, what have you. So there is a lot of research going into making those batteries multifunctional, such as wearable in clothing or flexible bulletproof vests. Right now, they put them on the sides away from the direct impact of shrapnel. But there is a lot of research going into that area. So again, the major feature of the conventional lithium-ion battery nowadays is the liquid electrolyte, which is based on highly flammable solvents, not only toxic, but they're also very flammable. And the electrodes are separated by this polymer porous membrane, and there are only few requirements on the strength of that membrane. And when then that membrane breaks, you have the contact between the electrodes of opposite polarity, which leads to the extremely fast discharge, which we call short circuit, and ultimately to fires. Many of us are familiar with these examples, but the one on the bottom right, I don't know if you can see my pointer there, that is actually the cylindrical cell from that spacesuit battery pack. So imagine carrying these on your back. So obviously safety is a big concern for the batteries based on the flammable electrolyte, and this leads to the very obvious advantages of solid state, where we replace that salt dissolved in organic solvents, we replace that with something non-flammable and solid. Typically it's a ceramic. And the benefits include wider temperature window, obviously. There is no toxic electrolyte to burn. There is no gassing coming out of such batteries. They are more tolerant to the abuse in case of impact scenarios and such. If you look at the diagram that I stole from Sarascon's paper, they allow using metallic lithium as an anode, which opens your potential tremendously, the voltage window for the battery cycling. And finally, the last 3 bullet points, you can reimagine the packaging because it's solid state, right? Because they're safe, you can use them in wearable technologies, and they have been used, as I will show in the next few slides. And finally, if you designed your electrolytes strong enough, you can use them potentially as structural batteries. That is something that doesn't only store energy, but also provides some support for the load in structures. So solid electrolytes. So here's, it's been in use surprisingly for a very long time, actually. And here is the question for the audience to see what you can guess. When was the first solid electrolyte introduced?
Perfect. All right. So everyone has heard the question, and your possible answers are on screen, and you can simply click on 1970, 1928, 1901, or 1831. And those are your possible answers. Go ahead and vote now. And I want to just give everybody a couple moments to vote and remind you that if you have questions for Serhii or Eric or Nian, please send those during the presentations so we can get to them during the Q&A after all of the talks. And looks like the majority of you have voted. So let's go ahead and close this in 5, 4, 3, 2, 1. Okay, Serhii, the results are in. 38%, which is the largest share, thought it was 1928, followed by 23% said it was 1901, 21% said 1831, and 19% said 1970. So what's the correct answer?
1831, Michael Faraday. So yeah, silver sulfide was the first solid electrolyte, believe it or not, over 100 years ago. And the The most recent example of all-solid-state battery is the lithium iodine battery that was introduced back in the 80s for the pacemakers, and it's still used for the pacemakers. So the solid-state ionics is quite an old field, and over the years, people have developed a lot of solid-state electrolytes with conductivities approaching those, ionic conductivities approaching those of liquid electrolytes. And this chart here shows, most probably people are familiar with commercial products, with garnets and maybe LATP, which is typically made. The major sourcer is a Hara Corporation in Japan. They make them in different shapes and forms. So lots of electrolytes to choose from. But the solid state is still facing an uphill battle. We have a lot of companies that work on this. Here are just a few examples. There is a lot of investment from the automotive industry into this. Factorial Energy is a good example, which has a lot of investment from Stellantis and Mercedes. But at the same time, the day for the large-scale production of solid-state batteries that can be included in the automotive battery pack keeps being pushed further and further away. So we have this goalpost moving from originally 2024 to 27 to 2030. I think Toyota now is planning to release something in 2030. So what seems to be the problem? We have huge choice of electrolytes, research, it's over 100 years of experience. What seems to be the problem? So to try to answer the question, Oak Ridge National Lab organized a workshop a couple of years ago where we invited over 30 participants from academia, industry, and national labs to share their ideas and their progress. And the results are available as this technical report, which everyone can download from OSTI website. That's where all the DOE government documentation goes. And the brief summary is published in ACS Energy Letters. So most importantly, if we look at the survey of literature and based on the feedback from the participants, we identified 3 areas that need most of the development. That's the mechanics, manufacturing, and practical cell design. And I will talk mostly about mechanics here. So based on my conversations with many of my colleagues, electrochemists, what we call battery people, there is definitely a need for a common language when we describe what happens inside the battery cell. Because whenever you have charge and mass transport inside the battery cell, it always results in dimensional changes in battery components or strains. And these dimensional changes, in case of solid-state batteries, are even more critical because there are there are more than 2, but 2 most critical differences between liquid electrolyte and solid-state batteries. Number 1 is that in liquid electrolyte, lithium can plate only on the surface of anode. If it's graphite, it will always plate on the surface of graphite. So that gives you at least some degree of control where to expect your lithium to appear. In case of solid-state batteries, it can plate inside the electrolyte, which is especially pronounced in garnets. It can just start plating in the bulk of the electrolyte. And the strain in the cathode particles can lead to the fracture of those particles, and in liquid electrolyte, they just lead to the increase of the surface area. In case of the solid electrolyte, that leads to complete loss of contact between the electrolyte and the cathode particles. So when electrochemists talk about concentration gradients, transport, cyclic voltammetry, we as mechanical engineers and material scientists hear fatigue, fracture, creep, stress relaxation, and so on, because all those processes can be connected together. And there are basically 3 major sources of stress in solid-state batteries. One is compositional strain in cathodes, which comes from the fact that whenever you intercalate or remove lithium ions into the cathode structure, which is again typically layer transition metal oxide, you change its dimensions and its volume. And when you do that in contact with the solid electrolyte, which is typically ceramics, that leads to the formation of the cracks, either at the interface or in the bulk of the electrolyte, as shown in this SEM image. So think about it as if you're making a composite material with particles and matrix having very, very different coefficient of thermal expansion, and then you try to warm it up. So the problem here is, in addition to the volume mismatch, is that those strains are anisotropic. The expansion typically happens along the C-axis of the crystal, and they're highly inhomogeneous. How inhomogeneous? Well, we have this special tool developed here at Oak Ridge called electrochemical strain microscopy. It is basically an atomic force microscope, AFM, with the conductive tip, and you can apply the bias to your tip and the substrate, which creates electric field, which in turn moves the lithium ions inside the crystallographic lattice, which in turn creates the strain. And that strain is measured by the same AFM tip. So in that way, you can get the strain fields on top of your fully dense cathode with nanometer resolution, really. And if you scan your, in this example, this is lithium cobalt oxide. If you scan some area, you will see highly inhomogeneous strains here. And again, because many things depend on how your lithium cobalt oxide crystal oriented with respect to the AFM, you can see some areas like area 2 here is totally silent in out of plane AFM mode, but extremely active in plane AFM mode. So that gives you some idea of how inhomogeneous and how complicated this map on the cathode can be. And that strain map directly transfers to the electrolyte, right? So the electrolyte should remain functional in contact with this cathode over many cycles, or otherwise, again, we get this interfacial cracks or through the electrolyte cracks because of those changes. Again, those changes are highly anisotropic. So how do we deal with that? How do scientists currently try to maintain this interfacial contact? Well, you will be surprised by applying huge amount of pressure to the laboratory electrochemical cells. To keep this interfacial contact together, usually the cells are cycled under pressure. And what kind of pressure? What does huge mean? Well, we can look through the literature. Here is one example. Beautiful cycling. You can see minimum capacity fade over many cycles. But look at the stresses applied, pressures applied: 50 megapascal, 75 megapascals. So if you calculate that over the area of your typical car pouch cell, right, that's going to be around 20 tons of weight that needs to be sitting on the battery to make it work. So obviously, for now, most of the prototypes work only in the small laboratory cells where the external pressure can be applied. And obviously, that external pressure is another major source of the stress inside the battery. The third major source of stress is from the lithium plating into the defects. And I will delegate the discussion of that to my colleague, Eric Herbert, who will be presenting this in way more details in the next presentation. So overall, the take-home message is that solid electrolyte is the component that connects positive and negative electrodes, and it is always under some stress. It has to deal with a lot of stress. I don't envy solid electrolytes. The problem is that the way to deal with the stress for most of the solid electrolytes that we have, they're ceramics, right? So the typical response to the stress is to crack under pressure, unfortunately. So these are the examples of what happens to different electrolytes from nasicons to LLZO when you introduce a sharp contact load into the electrolyte. The response is usually formation of crack. That's their way to reduce the stress. And there is a relatively simple reason for that. In crystalline ceramics, the energy penalty to create dislocations is really large because of the typically large Berger's vector. So the response to the load and usually is fracture because it's more energy favorable. But if we look at other class of materials that is somewhat under-researched, glasses are way more interesting because in addition to responding by cracking, they have two other mechanisms to respond to the applied stress, right? It's densification and shear. And depending on the combination of these two, we can have actually relatively ductile glasses when it comes to the stress state at the nano and micro scale level. So they have two other mechanisms in their arsenal to respond to the load. Unfortunately, most of the commercial glasses are still brittle. This is the typical example of what happens in borosilicate glass when you apply non-indentation to it. And the reason for that is very simple, because most of the commercial glasses are highly networked, meaning that the tetrahedra are typically connected into this highly networked structure, which constrains the structure to the point that it prefers cracking as opposed to flowing in shear. They can densify, but flow in shear is a little bit more tricky. There is, however, a special class of glasses where optics is heavily involved. They're called either ionic glasses or inverted glasses. Inverted glass basically means that you have higher amount of glass modifier compared to the glass former, which means that your tetrahedra are not as connected as in a network glass, and it gives some flexibility of sliding with respect to each other under the load. They typically have lower viscosity and decent ionic conductivity, but most importantly, mechanical behavior somewhat similar to bulk metallic glass. And the good example is lithium phosphorus oxynitride, which was developed at Oak Ridge here. Oak Ridge Lab, we call it LIPON as short. And again, you can see this phosphate tetrahedra. Some are connected through the bridge in nitrogen, some are floating in this, if you will, soup of lithium and free to move in shear. And LIPON has been demonstrated to cycle extremely well in solid state thin-film batteries, tens of thousands of cycles applied with minimum capacity loss. But more importantly, it has kind of remarkable mechanical behavior. So this is the snapshot of what happens when you indent LIPON with very sharp nano-indenter in introducing the high intensity stress state here. And you can see instead of cracking, it prefers to flow outside in shear, again creating this pretty large pileup at the edges. And most likely the densification occurs as well, allowing it to resist cracking. When we tested a lot of electrolytes, we were unable to introduce cracking by non-indentation in LIPON. So at least at the strain rates examined here and at the length scales examined here, LIPON is pretty much immune to fracture in our experiments compared to the other electrolytes. So to wrap it up, give some conclusions and transfer to the next event. Solid state ionics has over 100 years of history and a lot of research, but the upscaling to large format is still, to quote Elon Musk, production hell. We cannot be applying the old approaches from liquid electrolyte batteries to the solid state batteries because it results in structures which can cycle only under humongous pressures to keep everything holding interfaces together. Electrolyte is absolutely the key component here, which connects two electrodes, and there are quite a unique requirements on its mechanical behavior. It needs to be sufficiently hard to work with lithium, but at the same time, it needs to be resistant to fracture. And we think, based on our experience, that, and not only us, glass ionic conductors are really worth exploring because they provide several mechanisms to avoid fracture. Plus, they don't have any grain boundaries, so the residual electronic conductivity is pretty much zero in these materials. And the question on how to deal with the metallic lithium and what we call dendrites, even though not all of us like this term, that the next presenter, my colleague Eric Herbert, will explain in great detail. So I'm going to go over the acknowledgement of the funding and my co-workers. And if there are any questions, I'll do my best to answer them at the end of this session. Thank you very much.
All right, thank you, Sergey, and we'll transition to our next presenter. That was an excellent talk, and we'll move on to Eric Herbert. And as Sergey said, Eric is a colleague of his at Oak Ridge National Laboratory. He's a senior staff scientist and mechanical and properties and mechanics group lead at Oak Ridge. His expertise lies in the systematic development of methodical, repeatable, verifiable, and hypothesis-driven experiments designed to fill critical knowledge gaps related to structure, property, process, relationships. Before joining Oak Ridge, Eric held a tenure position as professor of material science and engineering at Michigan Technical University. He spent more than 10 years in industry with Nano Instruments, Inc. Eric earned his PhD at the University of Tennessee, Knoxville, under the guidance of Warren C. Oliver and George M. Farr, both of whom are international visionaries and pioneers in the field of small-scale mechanical behavior and nano indentation. And with that, I'll turn the floor over to Eric and let him begin his presentation.
Okay, so slides are showing up and you can hear me okay?
Looks great.
Okay, great. All right, well, thank you very much, Bill and Sergey, for the great setup there. So at any rate, I'm grateful to be here today and to have an opportunity to share with all of you some of our work in trying to understand some of these hidden surprises of lithium metal's mechanical behavior, and then, of course, the implications of those surprises for the development of solid-state batteries. Right? So before I dive in, just want to say thank you to a number of collaborators here, of course, Sergey, Andrew Westover, Nancy Dudney, Stephen Hackney. Steve in particular was one of the key drivers behind a lot of the heavy lifting in our lithium program early on. So to all of these folks, just a big shout out to say thanks. This has very much been a team effort over the years. All right. Okay, so as Sergey said, what I really want to focus on is the mechanics of lithium metal, right? And in particular, what's going on at battery relevant length scale. So one of the most important aspects of understanding the mechanical behavior is connecting with this idea of a mechanism of action, right? So I'm going to go a little over the top here and try to illustrate this point with this sort of silly cartoon here. So the idea is we're going to pretend that you've befriended this alien here, and he's offered to fill your car with gas, right? Now, it turns out the alien understands the idea of burning gas to access its stored energy, but he has absolutely no idea how the gasoline is physically used, right? So he unwittingly fills the passenger compartment of your car with gas, all right? So our buddy here has made a pretty poor choice because he's unaware that the mechanism of action that controls the energy conversion required to move your car down the road is the internal combustion engine, yeah? All right, so building on that basic analogy, what I want to do is try to just get a handle on the basic mechanisms of action that control the mechanical behavior of lithium metal. And in particular, as I said, what we're interested in is basically the operational efficiency of these mechanisms at battery relevant length scales, all right? So to get you thinking along those lines, here's a simple statement to consider. So true or false, all right? So the strength of a metal is an intrinsic material property. And by intrinsic, I just mean that, short of something like porosity, the strength doesn't depend on the processing conditions, yeah? All right, so you only got two options here. In the first one, the statement's taken to be true because the strength of a metal is uniquely controlled by the chemical bonding between the metallic ion cores. And of course, that bonding is independent of the processing conditions. And then in the second option there, that statement is false because strength depends on microstructural defects, and those defects are something that can be controlled through processing conditions. So Eric, I'll let you run the poll there, and we'll see what the crowd comes up with.
Perfect, and they're already voting, so we'll just give them a couple more seconds. About half of you have voted, and it's a simple true or false. And simply click on the radio button on screen And let's go ahead and close this poll in 5, 4, 3, 2, 1. Okay, Eric, the results are in. 72% of the audience, which is the largest share, said false, and the rest said true. So what is the correct answer?
Okay, the answer is false. That is correct, right? So strength is all about defects, and in fact, we can tune the mechanical properties, in particular the strength of a lot of alloys by several orders of magnitude just by monkeying around with the defects through processing. So processing is king when it comes to at least the strength. Yeah. So for those of you that missed that and got true, then I think you'll learn a lot, or I hope you'll learn a lot as we go through the slides here and just try to understand what's going on with the mechanisms behind the mechanical behavior here. All right. So let me see here. I've gotten into a viewer that my back. Okay, there we go. All right, so this image over here on the top left is just a schematic of a solid state battery. Below that is just this zoomed in rendering of this interface here between the lithium anode and our solid electrolyte separator. Yeah. And so during charging, the lithium ions are obviously traveling through the separator. And in a perfect world, we just plate one atomic layer at a time of lithium back to the anode, right? But in reality, what we end up getting is this preferential plating that occurs within these morphological defects here at the interface between the anode and the solid electrolyte separator, right? Now, within those defects, we're basically just, we're stuffing in, we're shoehorning in more and more lithium, right? So what we're basically doing is we're just compressing the lattice parameter of the lithium metal within those defects, right? And in doing so, we create this localized stress concentration, and that stress can get high enough to actually cause the separator to fail by fracture, right? And when you think about trying to develop a mechanically stable interface, that fracture is the bad actor here. That's the stress relief mechanism that we are desperately trying to avoid, all right? So in order for us to get some sort of handle on the pressure that develops within these morphological defects here at the interface, we basically turn to mechanical properties and mechanical behavior, right? And so in general, mechanical properties are what give us the ability to predict how a material is going to respond when its boundaries are mechanically loaded in some fashion, right? And I'm going to let the cat out of the bag here a little bit, because one of the really key pieces of the story here today, at least the story for me, one of the things I'd like you to remember is that we can't use the mechanical properties of bulk lithium metal in order to engineer mechanically stable interfaces, or as the slide points out here, to solve what Sergey pointed out about solving the dendrite problem. Yeah. So the reason for that is that the bulk properties of lithium basically don't reflect what's going on at these relatively small length scales here within these morphological defects, okay? And so it's just that the mechanical behavior, the mechanisms for driving that mechanical behavior change significantly, right? And it's not only a function of length scale, as it says here in the slide, it's length scale, strain rate, which is analogous to the current density, so it's about how fast you want to cycle or how fast you want to charge your battery, right? And then temperature is also going to be a key role in that, okay? So the bottom line is that in order for us to solve the dendrite problem, to create these mechanically stable interfaces, we really need to understand the mechanism of action that controls the mechanical behavior, right? And again, we're interested in what's going on at these battery relevant length scales, okay? And so that's where we're really going to look to try to understand and solve the dendrite problem. Okay, so this slide is a bit on the tutorial side of things, but it really does help pave the way to understanding the mechanisms that control mechanical behavior, all right? So the mechanical properties are measured, right? And so we often extract those properties from a uniaxial stress strain curve, like this one in the center of the slide, right? So that curve is basically just a mechanical fingerprint for the material. And so I'm not going to get into the details here, but the basic idea is that we're going to use a setup like this over here on the left. And basically, we're just going to pull our test specimen apart. And as we do, we record the stress, which is just the force normalized by the cross-sectional area, and then the change in length normalized by the original change in length, all right? So at time 0, the metallic ion cores are all in their equilibrium positions. Everybody's in their happy space, yeah? All right, and then as we apply the load, the stress increases, and physically, we are now stretching the bonds between the atoms, right? So that's what this gap represents here, okay? And then eventually, the stress becomes large enough that it triggers a transition from just stretching the bonds to both stretching, breaking, and actually reforming the bonds as well, right? And so that trigger is basically the master switch on the pressure release valve. And that stress relief is enabled by the shearing of adjacent planes of atoms. They're just sliding past one another here, okay? And so then when the load is removed, we get the elastic stretch back, but the shearing of the planes is permanent, yeah? All right, so from there, tell you what, in the interest of time, let's skip over the ductility here. Let's just cut straight to the elastic modulus and yield strength. These are two of the most important properties that we need in order to be able to have some idea of how to understand what's going on with the pressure within those morphological defects, all right? So the elastic modulus is an intrinsic material property, and that's because for a fully dense material, it's basically just a function of the chemistry and the composition, right? It doesn't depend on the processing conditions, right? And so the modulus is just defined as this slope here of the linear elastic portion of the stress strain curve, right? Now, yield strength, on the other hand, that is an extrinsic material property because in addition to chemistry and composition, it also depends heavily on the processing conditions, right? And so the important takeaway message here is that the yield strength is, again, it's that master switch on the pressure release valve, right? Because that's what triggers the transition from elastic to elastic plastic deformation, all right? Okay, so toughness, this is another important property, but I think in the interest of time, I'm going to motor past that one as well, all right? And so here we go. This is now what the uniaxial stress strain curve looks like for bulk metallic lithium, and it's given to us as a function of temperature, right? Now, it turns out that lithium is highly anisotropic. So the elastic modulus, as you can see here, it actually ranges from about 3 to 21 GPa, depending on the crystallographic orientation of the individual grains that make up the bulk metal, all right? And so, as you can see at room temperature and above, so that's these three curves here, right? The yield stress for bulk metallic lithium comes in at about 0.5 MPa or less, right? And so physically, that's telling us that we could pretty easily cut lithium metal with just a kitchen knife, all right? So now let's take a look at this micrograph in the bottom here. So here we're looking at a cross-section separator that's been cycled to failure. And as you can see, the lithium metal has penetrated all along the grain boundaries of this ceramic separator here, right? And so this is kind of a puzzling observation, not kind of puzzling, it's really puzzling because the stress strain curve up here says that bulk lithium metal is basically soft as butter. So it's not clear at all how lithium metal can support the pressure that's required to propagate along these grain boundaries of a ceramic separator, yeah? And so an intuitive solution would be, well, let's just get rid of the grain boundaries, right? They clearly must be the weak spot. We'll just make a separator out of a single crystal. Well, they've gone down that road, and lo and behold, the outcome is exactly the same. The lithium just finds another defect to exploit instead of the grain boundaries, okay? All right, and so here is another apparent paradox. So this plot shows the hardness as a continuous function of depth, and it's over the range of about 40 nanometers out here to a micron, right? So I'm not going to get into the details here, but the conundrum is that based again on this uniaxial stress strain curve for bulk lithium metal, the hardness at room temperature should be coming in at around 3.5 times or so the yield stress. So something like 1.5 MPa, right? And yet here we are, take a look at the numbers on the y-axis, right? We're, as much as, 2 orders of magnitude higher. So again, the million-dollar question is, how on earth does lithium support these high stresses, yeah? All right, so I'm gonna offer a potential explanation, right? But before I do, I wanna loop back to this idea of rigid slip in bulk lithium, right? And this would apply to any, bulk crystalline metal here. All right, so the idea there, at least what's pitched by this cartoon, again, for a bulk crystalline metal, this image actually does an okay job of illustrating what we observe experimentally, all right? But it turns out that this idea of rigid slip, which would be analogous to the shearing of this deck of cards, right? that mechanism is the wrong mechanism of action. We know it's the wrong mechanism because the theoretical yield strength associated with rigid slip, right, that's calculated here, these numbers are orders of magnitude higher than what we observe experimentally, right? So that's telling us, hey, you got the wrong mechanism there, all right? So turns out the correct mechanism is something called dislocation glide, you know? And so the operation of glide requires a planar defect in the crystal. And so we refer to that as a dislocation. And the simplest version of a dislocation is analogous to an extra half plane of atoms basically just being stuffed into the lattice, you know? All right, so this image here is a bubble raft model. And if you look at it closely, you can find the dislocation. So I'm just going to highlight that for you so it jumps off the page, all right? And so over here on the right is just a simple animation that illustrates the difference between rigid slip and dislocation glide, all right? So click the button, hopefully that works. All right, so rigid slip requires simultaneously breaking all those bonds along the glide plane. And that obviously requires a lot of energy, you know, hence these high theoretical strength limits here associated with rigid slip, right? So in comparison, dislocation glide operates very differently. And in this case, we achieve the exact same outcome, but it only requires breaking the bonds along the dislocation core, right? And so that mechanism requires much less energy, and that energy is consistent with what we observe experimentally up here, all right? Okay, so now let's go back and, you know, we're taking a look at our two apparent paradoxes here. And so we can't effectively rationalize these observations using rigid slip or dislocation glide, right? So it's pointing us in the direction of, you know, there must be something else, right? And so this additional mechanism that we need, we're going to propose that that is stress-directed diffusion, right? And so let me explain why. So at room temperature, we're at about 68% of lithium's absolute melting point, right? So that means even at room temperature, the lithium is constantly annealing. So the dislocation density is just decreasing with time, right? And so at these relatively small length scales over here, right, the self-limiting behavior of lithium just becomes a statistical mechanics problem. It's all about the probability of finding or not finding the mobile dislocations or the active dislocation multiplication sources within these small constrained volumes of lithium metal, all right? So the bottom line here, the key takeaway is that when dislocations aren't available within that stressed volume of lithium, right, then glide becomes inoperable. So we take that mechanism away, the lithium's got to find some other way to alleviate the pressure. And one way to do that is through stress-directed diffusion. And that diffusion is going to be driven by the gradient in the elastic strain. Basically, it's that non-uniform compression of the, you know, lithium's lattice parameter, right? We talked about shoehorning more and more lithium into these morphological defects at the interface. So that's what produces this gradient in strain, okay? And so conceptually, this mechanism, stress-directed diffusion, just works like this kid's game here that allows you to move the numbers around and put them in order using the empty hole there, right? So in the case of lithium, it's going to use the vacancies in the lattice in order to transport matter away from the stressed volume of lithium, okay? And so that mechanism, it can work quite well, but in general, it's nowhere near as efficient as glide, right? And its efficiency depends significantly on three factors. I'm sorry, I should have put them on the slide here, but first one is basically, it's all about how fast you're trying to move lithium out of the way, right? So it's going to be related to our current density, and again, how fast you want to charge your battery, right? Second factor is going to be how far you're asking the lithium to move, and so that's going to be effectively related to the diffusion length, and then the third factor is going to be temperature, okay? All right, and so where this ends up leaving us then is it paints this picture of a very important competition for stress relief, and that's occurring nominally between three different mechanisms, right? We got our stress-directed diffusion, dislocation-mediated glide, and then the one we're desperately trying to avoid is fracture, all right? And so that competition creates something of a Goldilocks problem for us, all right? So the idea here is that we've got lithium ions that are preferentially plating into any non-planar regions of the interface, right? And so the pressure builds inside that defect until one of those stress relief mechanisms is activated. So diffusional flow, glide, or fracture, right? Now, big morphological defects like this one here, right? These pose less of a threat because the stressed volume is big enough to have a high probability of finding the mobile dislocations or the active sources that are required to keep the pressure low, right? Keep it close to that half MPa number, right? At the other end of the spectrum, small defects like this one here, these also pose less of a threat, right? And it's because the defect is small enough that diffusional flow can act as an efficient stress relief mechanism, okay? So it's the morphological defects in between these two limiting cases that are going to be, between these two cases, that are going to be the potential problems, yeah? And so the key issue here is that, defects that are in between those two limits, right? Those defects are too small to have a high probability of finding mobile dislocations, but they're too big for self-diffusion to provide efficient stress relief. And so under those conditions, that's what enables the pressure to climb, potentially get as high as 100 MPa or more. And so those stresses are potentially capable of enabling failure in the separator, right? Fracture of the separator, okay? All right, so this is the last slide here, and so basically this is just a summary here that explains how we currently think about engineering mechanically stable interfaces in our solid-state batteries. Yeah, so as I hopefully have made very clear, the key issue is that the self-limiting behavior of lithium, it changes radically at battery-relevant length scales, right? It can support more than 100 times its bulk yield strength when dislocation glide is inoperable, right? So in terms of engineering next generation materials, the name of the game is going to be figuring out how to control that competition for stress relief. And we're going to do that by engineering the structure property relationships so that we can get efficient stress relief mechanisms operating over the widest possible range of battery relevant length scales, strain rates, and temperatures. So for our metallic anodes, that's going to translate into exploring surface coatings, treatments, possibly adding alloying elements, or figuring out how to engineer other unique microscale ductility mechanisms, right? And then the last point I'll make is that we obviously need modeling tools that accurately capture these stress relief mechanisms that are operating not only in our anodes, but obviously in the separators. And I didn't emphasize it at all, but obviously the anode is paired with a separator, right? And so all these problems that Sergey was talking about with the separator, well, it's because of what the lithium is imposing. And so the separator plays an absolutely pivotal role in trying to figure out how to alleviate that pressure that develops in the lithium, and ultimately how to keep a mechanically stable interface. All right, so I will end it there, and look forward to your questions at the end.
Okay, thank you, Eric. And we'll move on to our third presenter, who will take us in a somewhat different direction. Nian Liu is an assistant professor at the School of Chemical and Biochemical Engineering, Biomolecular Engineering at Georgia Tech. He received his BS in 2009 from Fudan University and a PhD in 2014 from Stanford University, where he worked on the structure design for silicon anodes for high-energy lithium-ion batteries. From 2014 to 2016, he conducted postdoctoral research at Stanford, where he developed in situ optical microscopy to probe beam-sensitive battery reactions. Liu's lab at Georgia Tech is broadly interested in the combination of materials, electrochemistry, and operando microscopy for studying global energy challenges. Specifically, his lab focuses on electric vehicle battery, and stationary battery sciences and technologies. Liu's publications have been cited over 30,000 times, and he is recognized as a highly cited author by Clarivate. He is the recipient of the Electrochemical Society Daniel Cuvicchiati Award, and 2014, the ACS Division of Inorganic Chemistry Young Investigator Award in 2015, Chemistry of Materials, up-and-coming researcher in 2017, Journal of Materials Chemistry, emerging investigator in 2018, the Jim Pope Create X Faculty Fellow in 2021, and Nanoscale Emergency Investigator in 2022. So let's turn the floor over to Neon and look forward to hearing what he has to say.
Thank you, Bill, for the kind invitation and introduction. I work at Georgia Tech. It is a university in the southeast of United States. I saw a lot of international participants, so I want to introduce the location of where I am and where I work. I see also in the chat there are some questions already on the grid scale energy storage, and this will be the focus of my part of the presentation. And so renewable power supply like solar and wind, these are having higher and higher percentage in our energy supply. But different from like a power plant, conventional power plant, these wind and solar energy fluctuates over time. And for example, the solar energy fluctuates on a day-to-day basis. And the wind energy represented by the blue color, they have a longer period of fluctuation. But in order to fully utilize these energy supplies, we have to have some kind of storage device that can store these renewable energy when they are abundant and supply them when these renewable energies are low. So there are many ways to store energy, and here I only listed 4 of them. The pump hydro, basically pump water up and down, and this way will associate with the release and storing of energy. But this technology has geographic limitation, and also it has environmental impact to the impact to the environment. And the second way to store energy in a large scale is gravity energy storage. For example, you can move heavy objects up and down, right? And when you want the energy, you move them down, and this will generate electricity. When you want to store electricity, you lift these pieces up and put on the top. And this is less impact to the environment, but it has relatively low specific energy. So you need to build a very large plant to store the same amount of energy. The third way is very popular right now, hydrogen. Right? You can use an electrolyzer to split water to produce hydrogen when you want to store electricity. And then the energy is stored in a chemical form. Right? You can even move hydrogen around, and you can store it for a quite long period of time. These are all the advantages. And when you want to use the release the energy, you just flow the hydrogen through a fuel cell, and that will be turned back to electricity. So the only problem of this is the round trip and energy efficiency is pretty low, lower than 50%. And this is kind of the limitation. So the last one is the main topic for today, which is the battery energy storage. I'm not saying this is better than the other, but it has its own advantage and uniqueness, and that's also my research expertise. And if we look at the scale of the grid scale energy storage, It's actually very, very large. And also it's different from the battery that you typically use in your phone, laptop, and also the electric vehicle. It has different requirements. For example, the cost of a grid scale battery has to be very, very low. I mean, $10 to $20 per kilowatt hour. Currently, the EV battery are almost 10 times that cost. And also, we want a very long life, right? Because this infrastructure, once we build it, we want them to last at least 30 years rather than 3 years, like a phone battery, right? And also the safety. Some of these facility will be near building or even inside a building. So, and they carry a lot of energy inside. We don't want them to have a fire hazard. So the safety has to be very, very good for these kind of batteries. And also we want the maintenance to be very low to save problems in the long term. And the scale is also very, very big. The existing lithium-ion battery production capability is around 3 terawatt-hour per year. And these batteries are mainly for use in electric vehicles. And to store energy for the grid, you need to consider the total energy consumption in the world. It's about 70 terawatt-hour per day. That's a huge amount of energy. And we, in order to achieve 80% renewable, that means 80% of these energy are produced from renewable. And because the renewable sources fluctuates, we need about 3 days of the storage capacity to enable 80% renewable. And 3 times 70 is about 200 terawatt hour. We need to install this much of capacity. And right now, we can only install at 3 terawatt hour per year. That means we need about 30 years to achieve this kind of capacity. But we already have the Paris Agreement, which aim to reach carbon neutral by 2050. So we need to actually accelerate this and install storage capacity at a speed of 8 terawatt hour per year in order to reach 200 by 2050. So it's very challenging, and that's why people are not only looking at the lithium, but also look at other technologies of battery, see which one makes more sense for these kind of requirements and the rate of deployment. So one of the biggest problem of lithium-ion battery as a grid scale battery is the flammability. And these pictures shows batteries, lithium battery catching fire. And these flammability is intrinsic because they use organic liquid electrolyte. We heard from previous speakers that if we can change the electrolyte, that is a way to actually improve the safety. As for now, a majority of the lithium batteries still use organic liquid electrolyte inside. So when we look at other alternative technologies, actually zinc becomes a very promising one. The primary zinc batteries have already been in the market for decades. They are very safe and have very high energy. They're used in hearing aid devices. And if you look at the theoretical energy density and the specific energy, the zinc chemistry actually they're pretty good. You know, some of them are even higher than lithium ion and approach lithium sulfur. And but their utilization and rechargeability are the main problems, much worse than current lithium-ion battery. So our research was to improve the rechargeability and utilization so that we can have a promising rechargeable and safe battery. So the commercial zinc batteries are not rechargeable. It can discharge, but then it becomes dead. So we did a lot of research to figure out what is the mechanism, why it dies, and how can we address this problem. So this schematic shows the formation of zinc oxide on the surface as a discharge product. As this covers the fresh zinc, it stops electrolyte from coming in. And then even you have fresh zinc under it, it cannot further react. And also zinc oxide is insulating, so it's very difficult to convert it back to zinc metal. And we even did a experiment. We fully discharged a piece of zinc and opened the battery to look at the cross section. You can see there are a lot of zinc metal still inside, but they cannot react because the outside is covered by the zinc oxide. And it's only about a 2 micrometer thick, and that's enough to passivate the fresh zinc inside from further reaction. So that's the problem. And another problem is that during the conversion of zinc oxide to zinc metal, it goes through a soluble species called a zincate ion. And this ion is soluble, so it can dissolve in electrolyte and move everywhere in the battery. And then you will have a shape change and also uneven deposition of zinc in your battery. So the active material is moving all the time, and that is another second problem. So we actually designed this kind of nano-sized zinc oxide electrode coated by ion-sieving carbon shell to address both problems I mentioned in last slide. First, the zinc particle is very small, so it's even smaller than 2 micron, which is the critical passivation thickness. So it will fully convert before passivation happens, not thick enough to passivate here. And then second, the carbon shell act as a barrier to confine the soluble zincate intermediate inside. So the things inside the particle will not go out and it's retained inside. So this will help keep the active material in its original location. And but this shell has to allow hydroxide ion to come in because that's necessary for the reaction to happen. And we actually did the synthesis, and you can see this is the particle size, very small, and it has the shell. And the shell is microporous, so it can block the zincate ion from escaping out. And we indeed confirm the confinement of the zinc soluble species inside of the shell by doing this dissolution testing. And a second work I want to talk about is the suppressing the hydrogen evolution, because the hydrogen evolution is a competing reaction with the zinc redox reaction. So we want to suppress the side reaction. So we actually evaluate different coating material on the zinc and find that the certain material that have low catalytic activity towards hydrogen evolution result in a higher Coulombic efficiency of the zinc anode. And the third example is the we still cannot keep 100% of the zinc species inside of the shell all the time. So if a little bit escape out, can we actively bring them back into the shell? And so this is the active management rather than passive encapsulation. We did imaging to see how the zinc plating happens. You can see it's very dendritic, and it doesn't grow uniformly. And when you strip them, some of them will peel off and detach and become dead zinc and never react. So what we did was to add a layer of a silver nanoparticle seed onto this substrate. Now you can see the zinc will preferentially grow on the where the silver is, and then this makes it very uniform deposition. And there's no zinc, a dead zinc formation, even in the stripping process. So this proves that you can actually actively manage where the zinc deposits by giving it some nucleation sites. And you have seen this before. The fluctuation of renewable power supply is over multiple days. And lithium-ion battery and also other types of battery, similar type of battery, they have coupled power and energy. When you increase the power, you increase the energy, the power also increase together. But that's not what we want for the large-scale storage. We want a multi-day battery rather than a multi-hour. So we don't need to increase the power. We just want to increase the capacity. So that's when the flow battery come in. And flow battery has separate power and energy. You can increase the energy by enlarging the tank and keeping the power the same. Right? And that's the beauty of flow battery. So the cost of lithium battery will look like this as you increase the capacity, but the flow battery look like this. When the battery is small, the flow battery is much more expensive. But if you have a high storage capacity with the same power, then the flow battery can be cheaper than lithium and other type of static battery. And I will skip this and directly show you this. What we invented is a microtubular flow cell for flow battery. This is what a typical flow cell look like for flow battery. They adopt a planar configuration, membrane in the middle as a two-dimensional membrane. And our device is a tubular structure, and the membrane is actually a tube. They look like this. These are 4 Nafion membranes, and inside you have 1 electrode, and outside the membrane you have another electrode. And the reaction happens on the 2 electrodes, and the ion pass through the membrane. And this is entire thing is less than a millimeter, about a half millimeter. So it's a very, very skinny tube, and you can bundle them together to form a bigger module. And the distance between electrodes become very small, and this is very good for the kinetics. And also membrane surface area in a given volume of the device is very large. And this is good because you can shrink the power module to very small, reduce the footprint, and reduce the cost. And you eliminate the flow distributor, and this will further reduce the cost. And we proved that the microtubular device has much higher current at the same cell voltage. So the device has very high volumetric power and volumetric current. That's the key advantage. So this is still ongoing work. We hope we can further enlarge the module size to include hundreds and even thousands of tubular membranes inside one module to make it push it towards the real product. This is my last slide. So I showed you what are the consideration of battery for grid scale storage. And also I give you two examples that my research group work on, zinc and the flow battery. And I would like to acknowledge the students in my research group that does the work, and also the funding agencies. I think I'll return the microphone to Bill for Q&A session.
Thanks, Neon. I wish we had about 2 hours given the quality and number of the questions that came in, but unfortunately we have to be somewhat selective and triage the questions. So I'll kind of pass them around and start with a question for Sergey, which is in conductive AFM. I assume the image is collected after the material is used. Was the image ceramics image before used to see if it was homogeneous in the beginning? And can you also do an in situ CAFM imaging to see a real-time crack formation?
Excellent questions. So this probably the title of this technique is a little bit misleading. It's called electrochemical strain microscopy, but there is actually no electrochemistry happening there. There is no redox reaction where the AFM tip contacts the electrode. It just applies the potential difference and redistributes lithium ions inside the lattice. And everything is measured in situ. So these are freshly made electrodes subjected to this potential difference, and we measure the strains with AFM tip. But there is no charge transfer at the interface. So.
Okay, and for Eric, we have really two questions that can be combined into one. One was, how might modified organic polymer serve as electrolyte to provide more molecular flexibility? And can conducting polymers be used as electrolyte in solid state batteries as an electrolyte?
So I guess my knee jerk is, yeah, that's definitely a very viable option, right? In terms of figuring out how to engineer stress relief capability, everything's on the table, and that would certainly be a potential contender. So there's definitely a lot of unique mechanisms that you have to take advantage of there to try to tune that you certainly wouldn't have in other classes of materials. So beyond speaking to specifics, I would just say, yeah, that's definitely a viable option.
Okay, and Neon has two questions again that can be sort of combined. What material was used to coat the zinc to avoid passivation? And does the coating reduce the redox reaction rate?
Yeah, so the coating we used was, you see in the presentation, in one case it's carbon, porous carbon. In another case, it's titanium oxide. And the function of the coating is to encapsulate the soluble zincate species inside. And it doesn't change the thermodynamics of the reaction. So the potential will stay the same, but it adds a little bit of weight to the material. So the specific capacity will reduce a little bit.
Okay. Jumping back to Sergey, how useful are computer simulations, DFT, MDML, in understanding solid state batteries?
Oh, extremely useful. The biggest problem is that typically the time scales that are required for the reactions to occur and diffusion to take place are much longer than what can be done with MD. But in terms of mechanics, a lot of questions can be answered by using MD simulations, simulating like unit deformations, be it tension or shear. Actually, we've utilized it a lot to explain the mechanical behavior of light on glass. So we've used a lot of MD simulations for that. So short answer, they're critical for development of solid-state batteries.
Okay. And by the way, any of you can jump in on one of these if the original question's been answered.
I see a cool question about. I see a cool question. Does the Earth battery count as solid state device? The answer is no. If the soil is completely dry, it's not gonna work. So your electrolyte is still water inside the soil. So.
Okay. This one's for Eric, and it looks like Eric's caught this one as being of particular interest. And it's wouldn't or couldn't a high entropy solid that includes a decent amount of lithium solve the stress problem? He might have asked this for himself. I don't know.
No, didn't ask it for myself. And I don't know the specifics of how well that would work. I mean, it's a really interesting question because the HEAs can do a lot to promote dislocation motion and hinder crack propagation, right? So, so anything you could do to, promote fracture toughness in the solid electrolyte separator would definitely be a wonderful thing. The key issue is that you've got to be able to pair that with a high degree of ionic conductivity. So I don't know, Sergey, any suggestions there? I've never seen HEAs used in that respect with solid state batteries, but I don't know. It would be an interesting thing to pursue if you could figure out how to also maintain a high degree of ionic conductivity. Any thoughts you want to pass along?
Yeah, so probably by high entropy, we assume created ionic glass with highly different ionic radii, right, of different constituents. Yeah. So that would probably create material with much higher density. So at least that would eliminate one of the mechanisms of resistant fracture by densification. Probably that would reduce the free volume. What that will do to the ability to deform and shear, that's an open question. As far as the ionic conductivity, most likely that would be promoted, actually.
Okay.
Okay. Interesting question for Neon, if you can comment on this. Is there a future for multivalent ion batteries, calcium ion batteries in particular?
Yeah, I think multivalent is a very interesting one. Like zinc is also a multivalent chemistry, and calcium is also one. And they have more abundance than lithium. I mean, the recoverable abundance, not in the ocean, but on the land. So you can get those elements in a more quantity, a bigger quantity in an easy way. So these electrode material still need to be figured out. What is the host material to host these ions? And also, are those reactions reversible? That's an important thing, right? Lithium ion is very reversible. So the other chemistry, they all face the problem of reversibility. So those things also need to be addressed. And that involves a lot of study, right? Like the solid electrolyte interface, what electrolyte do you use? So yeah, a lot of research going on in a lot of elements of the battery. But yeah, I think it's possible that one of them will someday become scaled up. Yeah.
Okay, and I'm going to take advantage of my position as moderator and ask my own question. And it's really for all three of you that in evaluating the utility of these batteries in commercial technologies, commercial application, what are the minimum requirements for charging, discharging cycles and stability?
Yeah, I can say something first. So like for electric vehicle, it's 1,000 cycles typically. For phone battery, it's even shorter cycle, maybe 300, 500. For vehicle, it's 1,000. For grid scale, should be even longer, maybe 5,000, 10,000 cycles. Yeah.
So it really is.
Oh, sorry.
No, I'm saying it's application dependent then.
It is, but one thing to add is that end of life capacity in car batteries should be 80% or something. So the same battery can still be reused for stationary energy storage after it's done its job in the car. So they're actually very long life devices if you think about it. Yeah.
Okay. We'll go to Eric here, and the question is, do we know if the mechanics of sodium are similar to that of lithium?
So in general, it's going to have the same sort of issues, right? Any crystalline metal that in the bulk, its dominant stress relief mechanism is going to be dislocation mediated flow. And so when you take that away, it's going to be dependent on something like stress directed diffusion. The one big advantage maybe for sodium is that room temperature is closer to its melting point than it is for lithium. And so that would enhance its diffusion behavior. But offhand, I don't know what the self-diffusion coefficient is of sodium versus lithium at room temperature. Sodium's quite a bit bigger than lithium. Sergey or Neon, do you guys happen to know what the self-diffusion coefficient is of sodium metal?
I don't.
Yeah.
Shame certainly I don't.
Sodium is bigger, so probably harder to diffuse than lithium.
Would be my guess, but fundamentally, it's going to have the same sort of issues. So you just got to figure out how to engineer the structure-property relationships in some way, modify it so that you can enhance the diffusion characteristics. And frankly, I think it's really hard to think about just the anode independent of the separator. Those two materials are going to have to work together with one another. I guess that's an obvious thing to say, but you're really going to have to pair the stress relief capability of the separator with whatever your anode material is going to be throwing at it. So it's a complicated problem. I wish it would be fun to talk more about the polymer one, that first question. I feel bad for not doing it a little bit more service, but there's just so many interesting opportunities to tune the mechanical behavior of a polymer. It's a really complicated problem, but there might be some really interesting avenues to explore. Well, there are some very interesting avenues to explore on that front. So I'm anxious to see what people come up with in the future for those materials.
Yeah, it's actually a repeating question for all of us. How come we did not discuss polymer electrolytes in our presentations? I've seen that question.
Well, that's a very good point. Yeah, exactly. Yeah.
It's a very good point. The problem with polymer electrolytes, most of them are still binary electrolytes, meaning you still have a salt somehow dissolved, right? So to maintain charge balance, you will create these concentration gradients across the cell, which means that limiting current density could be quite low for this electrolyte. Their electrochemical stability, things like that. But Eric, you're absolutely right. Playing with the mechanics of polymers would be quite interesting.
Okay. The question specific for Neon, which is, what is your flow battery chemistry? Vanidates, ferrocyanates, cyanides, or others?
Yeah, that specific data I showed the voltage versus volumetric current density. That is measured using zinc iodine chemistry, but the device is independent of chemistry. So we have also tested a a lot of vanadium. We also test the quinone and the bromine, these other chemistry.
Okay, I think I like zinc more than bromine in my house.
Yeah.
All right, and I'll come back to Sergey. There were questions on the best ionic conductivity of glass electrolytes and how do we vary the viscosity of glass ionic electrolyte.
Oh, awesome questions. Well, when we say glass electrolytes, really what's available now is LiPo only, because right now there is no way to make glasses with such a high concentration of alkali ions by typical bulk production glass methods. So LiPo approaches 10 to minus 5 Siemens per centimeter in terms of ionic conductivity, but it can be made by sputtering, RF magnetron sputtering to the thicknesses of close to 1 micrometer. And because of its mechanical properties, it's enough to work in thin film solid-state batteries.
Okay, and we're kind of coming to the end here, so I'd like to give each of the three of you an opportunity to share any final thoughts they had. We'll kind of follow the same order and start with Sergey, Eric, and Neon.
So the final thought, this production hell can only be overcome in terms of solid state. That's the only thing I can comment on. When we shift our thinking about battery production from thinking that we can make solid state battery using traditional liquid electrolyte battery manufacturing, when you have cathode, anode made on a separate production lines, and you sandwich it all together with separator and fill it with the electrolyte, and somehow it's going to work. It's not going to work in solid state. You have to build them component by component and make sure they all work together.
Eric?
So I guess my parting comment would be that, at least in relation to just the solid state stuff, right? That's all I'm speaking to. The mechanics are going to be dictated by what's happening at battery relevant length scales. So as I said in the talk, you really can't solve the problems associated with engineering mechanically stable interfaces by exclusively looking at the bulk properties of lithium metal, or whatever your anode material is, whether it's sodium, you pick it. You really do have to focus on what the unique mechanisms are and how those change with the length scale and strain rate and temperature conditions.
Okay, thank you. Neon?
Yeah, so I think battery research is a pretty interdisciplinary field. And you can see in today's talk, we have talked about the mechanics, we talk about the chemistry, we talk about many rheology, these kind of things. So, but it has a very clear ultimate goal, right, to build a better battery for the future. And I think it's never too late for anybody to jump into the field to contribute something. And you can contribute from whatever your expertise is. So there are a lot of opportunities in that. But we also always need to consider how practical is this in the real field. And the practical relevance should always be in mind. Yeah, I'll stop there. Yeah.
Well, I congratulate the three of you for an excellent and informative talk. And with that, I will turn it back to the other Eric H. for closing remarks.
Well, perfect. I want to thank all of the panel and the moderator for an excellent event. Next time around, we'll have to talk about polymer electrolytes. The Science History Institute collects, preserves, interprets, and shares the past by exploring lesser known and sometimes overlooked stories from history of science and technology. They dive deep into the history of scientific successes and failures with a focus on expanding knowledge and broadening our understanding of how science and society intersect. Find out more about their mission and how to plan a visit by clicking the link in the chat. Now, there are more great upcoming webinars, and we'd like to invite you to join us. On March 28th, join the recently retired Dave Soroden of the American Chemical Society as he provides practical guidance in addressing some of the legal and financial challenges that retirement poses, like how Social Security and Medicare will impact your retirement, and the often neglected steps that will move you seamlessly into the next process and phase. Artificial intelligence and robotics are transforming society at large, and these groundbreaking tools will also accelerate chemistry research to new heights. On April 12th, join Alan Aspuri-Gusic, a professor of chemistry and computer science at the University of Toronto, as he discusses the rapidly growing field of self-driving laboratories. And finally, historical paintings are also complex chemical objects, so museums turn to analytical chemistry to decipher the mysteries concealed within their mycometric paint layers. On June 20th, join Victor Gonzalez of the French National Center for Scientific Research as he details how an unexpected inorganic compound was detected via cyclotron probes in Leonardo da Vinci's Mona Lisa. Because people like you create great chemistry, you belong here. Become an ACS member to network locally and globally with other chemists. Take the next step in your career, stay in the know, and keep up with chemistry news and research. We love to hear what you thought about our program. You can reach out to us through the ACS social media channels on Facebook, Twitter, LinkedIn, and by email at acswebinars@acs.org. We are curious to hear what you thought of today's broadcast. A short survey will pop up directly after the webinar that will just take a moment to complete. Also remember that an invitation email to view the recording of today's presentation will be sent to all registrants for a 24-hour period, after which it will be removed, edited, and added to the ACS and SHI websites. And that wraps up our program for today. On behalf of all of us here at the ACS Webinar Studios in Washington, D.C., and the Science Institute in Philadelphia, thank you so much for joining us, and we hope to see you in 2 weeks.